Hey everyone, let's start with another lecture of CS2505. Today what we're going to learn is compilation and linking, like how the compilation process works and how the linking is done and everything. You have already seen the intermediate steps of compilation. Today we will be looking at the more detailed stuff. Okay, so you have already seen how these steps work. The first one is you write a text file, right, your source code, and then you compile it. If you compile it with -s, where s is the capital, not the small one, then you get the assembly file. And if you put the assembly files together, you get the object file. And then if you put the linker, you get the actual executable file, right? And what linker does is it takes the libraries, like system libraries and stuff, and puts them together, so you have an executable program. You have already seen the intermediate steps and you have seen the whole process. Now we are going to take a look at more detailed stuff, which is how to actually organize your files in different files. So if you remember, Java has the concept of packages, like you put them in different folders and then you use like the package system or package scope. If you remember those concepts, this is going to be much similar to that, but not exactly. So yeah, I'll try my best to explain it. And again, if you have any questions about it, like if you do not understand any of this, let me know. Okay, I will try to give you more better examples so that you can understand it more. And again, if you want to follow this lecture, there is the codes available in the link. Download them and then try to go with me. Okay, so a typical C program organization is for a very small program, code is often organized in a single source file. The most common convention uses the extension C for the C source codes. Okay, um, in your first assignment, maybe you have seen, like in your C assignment, you have seen that maybe you have only a main file and that's it. But in bigger projects or bigger assignments or whatever, you will see that they are divided into multiple files. They will have multiple C codes and multiple object files, and they are all put together into one executable. You will learn that eventually, but let's go with the multiple C files for now. Okay, so for more interesting C programs, the code is typically organized into a collection of header files, which has the extension of H, the source and the source files, which are the C files, sometimes object files. In most cases, the header files contain only the type declaration and function prototypes, while the C files contain the corresponding implementation. So it may look like something like this. You have a main.c file, you have the header files a.h, b.h, z.h, and you have their implementation in the C files. Okay, the include directives, the hash include directives are used within the both H and C files to import declaration as necessary. The build process, pre-processing. Okay, the C preprocessor will load the contents of hash included header files into your .c file. So if you put something like in your a.h, if you have something like include b.h, it will actually replace everything. Like it will replace the hash include b.h with the content over here, and we have the void b and we have void c, right? So in our main.c, we have like include a.h, include c.h, and over here we need to include this as well, because without the function declaration, it doesn't know where to get well, the declaration. And the preprocessor's work is to replace this with the content. So this will be replaced here, and all of this will be replaced by a.h. So the whole thing will replace the a.h, and c.h will be replaced here. Okay. So the build process inclusions. Okay, so this is what the code will look like after the pre-processing. The include, like hash include, will be removed and they will be replaced by whatever content was inside there. Okay, so why would b.c include b.h? Maybe b.h includes the standard headers needed in b.c. And perhaps like b.h defines a type needed in b.c. You will be seeing that more later on, but this is more of a general like example of how it may happen. But like, I hope you understand, like, why do we need the b dot this part in our file b.c? Because like it's literally the declaration all over again, right? We have this and then we are implementing it all over again. So why do we need this? Maybe some of the library functions were declared in the b.h, and that's why we are putting that here. For example, in our b function, we might write the printf. But for printf, we need the hash include stdio, right? So maybe this was declared inside our b.h, and that's why we need to do include b.h. And there is another thing like type maybe were declared there. When you learn structure, it will make more sense. Okay, so let's see how the compilation process works. So the compiler processes each .c file separately from others. Okay, so they will have their own object files. Main.c will have a main.o, a.c will have a a.o, b.c will have a b.o, c.c will have a c.o, and later on they are actually combined into one object file. So whenever in main.c we are calling like a, it goes back to the declaration which was in the hash include, and then it will work same way for all of them. And what happens is then it goes and looks for all the other object files that are included in the compilation. So when a is called, it will go to the file a.c or a.o, which is the object file. B will go to the b.c, C will go to the c.c, and we see that this G is actually provided in this file, so it won't go to a different object file, it will just take a look at itself. Okay, so there is a problem. For some calls we must bind to code that's actually in a different object file, and that's how most of the projects will be. Like they will not be in the same file, they might be in different file like a.c, b.c, c.c. So that part is taken care of by the compiler, but you have to tell the compiler where that file is. So what main.o does is tells the compiler a tag, like gives it a tag saying that for each call from main.c to an external function a, b, c, because they are not included in the main.c. And what it happens same for a.o, because like it is calling to b, but b doesn't exist within this file, it has to go somewhere else, which is the b.c or b.o. So after all the dependencies are resolved, then what linker does is it's the job of the linker to combine the separate object files into one executable file. So it will take all the dependencies, it will take care of all the tags and put them all into an executable file. And that's why without the linker, your executable file is not complete. So that's a very messy process of the C compilation. And okay, so if you're worried whether it's going to be in the test or not, it's not going to be in the test, but this is an important concept you need to know for the rest of your life. So once again, to put them all into like some sort of review. So what happens is if you are having different files for each of your function, what you should have is first you should have, of course, a main file. it doesn't have to be named main.c, but it needs to have the function main, because that's where all of your compilation starts. You can put them into different files like a.c, b.c, c.c, and so on. And each of these implementations should have their corresponding header file. You can put them all into one header file. Like, for example, you can write something like my header .h, and you can put them all into one. It's up to you, but there might be some sort of like dependency issues, or like double declaration or something like that. You do not want to deal with that. So it's best if you have different header file for all of them. So a.h, b.h, c.h, and later we will see how to resolve whenever there is some sort of like double declaration or something like that, like duplicate declaration or something like that. But anyway, they should all have their corresponding header file, and those header files should have their declaration and some sort of like documentation, like what the file does and stuff like that. It's just comment, it's for better practice. It's not required, but it's something you should be doing whenever you're working in the industry. Okay, so what happens is whenever main starts executing, if it has any sort of function that is in a different file, like an external file, it will tell the compiler that maybe this file belongs somewhere else. And later, the compiler, when it puts everything together in the executable file, it will go through all the files that were included, check whether the function exists there or not, and then put them all together into one executable file. So that's how the whole compilation process works. You should try to run it by yourself, and it will make sense. In the end of this lecture, by the end of this lecture, I will give you an example of how to do that. You should try it by yourself to have a better understanding of what is happening. Okay, so you can actually do some sort of like controlling access. It is kind of like the private class in like private directive in Java, but not exactly the same. So often a.c file includes some functions and other things that are needed only in that file. And in that case, like for example, b function calls for a function called helper, but no other function outside of the file b.c does that. Okay, so for that we put the declaration helper inside the b.c before any calls to it, and make it static. So if you make it static, no one else outside the file will be able to access it. So it is kind of like a private function, and it only belongs to every function that is declared within b.c. And we do not declare helper in the b.h. b.h will not have a declaration of the helper function. Okay. Over here, as you can see, b.h doesn't have any declaration for the helper function. Okay, so the multiple inclusion problem, or the duplicate declaration, as I mentioned just a while ago, it is possible to create some unfortunate solutions. For example, here the preprocessor will copy the text, like over here, the preprocessor will copy the text of b.h into main.c twice. Okay, once due to the inclusion of a.h, and once due to the explicit inclusion of main.c, implicit inclusion in main.c. We are doing that because in a.h everything is supposed to be replaced by whatever is over here, and over here we actually include b.h, so it's going to be declared here twice. Okay, this scenario is difficult to avoid in large projects involving many individuals or teams. However, there is a simple fix using a preprocessor directive. The preprocessor directive is if not defined ph, define ph, then we declare whatever we want to declare, and then we end if. So this hash if and def is a preprocessor. preprocessor directive. It is kind of like hash include, but what it does is it tells the compiler if whatever I am writing over here is not defined before, then compile the rest of the stuff till it reaches end diff. Okay, so basically this part will be compiled if it was never declared. So what happens is at the beginning of the code, BH was not defined, right? So it's going to compile the rest of the stuff. Then it finds this one. And now it is defined. Then rest of the stuff are done and it stops here. So this is compiled once, but the next time when we are trying to declare it again, it will take a look over here and it will say that, hey, it was defined before, so we are not going to declare it again. And thanks to that, because of this a.h, it is included here. All of this stuff are compiled. Then when it gets here, it basically goes to this line and it tells the compiler, hey, it is already defined, so I'm not going to compile the rest of the stuff. So by doing this, you are actually making sure that it is not declared twice. If you look at the system library header files, you will see that most of them has some sort of these settings, so that even if you put stdio, like hash include stdio in multiple files, it will never say that it was declared twice or something like that, because it has a guard like this. Okay, so let's take a look at actual example. This example is given to you in the GitHub link. Download it and try to follow with me. So here's a short test driver, a Fibonacci function in a second. In a sorry. Here's a short program with a test driver, a Fibonacci function in a second file, and a header file containing the declaration needed for the Fibonacci function. So this is our driver file, driver.c. Over here we have a main function where we are running a loop till 50, and then we are calling the function rFibonacci.i. Our Fibonacci I. And where do we find it? We have declared a user-defined file over here. Okay, so this is important. Whenever you are declaring a user-defined header file, instead of these brackets, you use double quote. Okay, double quote basically means it is a user-defined header file. But if it says a bracket, it means it's a system header file. Okay, this is very important, and you should make sure that whenever you are doing a user-defined header file, make sure it's a double quote. Otherwise, you will face some errors and your code will not work. Okay, so yeah, over here we are declaring this function into a file called rFibonacci.h. So and we have a file called rFibonacci.c where we are actually implementing it. Okay, so this is what our implementation of the function rFibonacci looks like, and this is what our header file looks like, rFibonacci.h. So as you can see, we did something like if and def, we are putting a name and then we are defining it inside of it. So what happens is at the beginning, it will actually compile this part. And if it is ever included somewhere else, it will not do a duplicate declaration. And thanks to that, you will not have trouble of that specific error. And if you want to try that by yourself, try removing these lines from the rFibonacci.h and see what happens. In this code, nothing will happen. It will work just perfectly. But if it is a bigger code, it will say that it was declared twice and it will stop working or something like that. So yeah, play around with it a little bit, okay? So to compile this code, we will be compiling like this: gcc -o driver. So this is our executable file name. We know that after -o, we name the executable file name. We are using the C99 standard wall W, it is replaced by W extra recently. It's up to you whichever you want to use, but using -W is definitely fine because it's a C code, it's a C compiler, and there is always going to be a backward compatibility. Otherwise, many of the legacy codes will stop working. Then we actually just define the name of the C files. If you notice here, we are not defining the .h file, okay? The .h file is not needed here. We just need to include our .c files, okay? So after you run it, you will see that a new file is created, which is this driver. So this is our executable file. So what it does is it goes to this header file and it checks whether the declaration and everything matches. And if it matches, it actually creates the file. If it didn't match, we would get an error saying that this declaration wasn't found or the function doesn't match, and it will not create the driver file. Like, sorry, this driver file wouldn't be created if there was any sort of error, okay? So you can actually see the intermediate object files as well if you want. In that case, while compiling, you should mention this -c. So in many of your assignments and later on in your life, you will be given object files instead of a C file. The main reason for that is nobody wants to give their source code to someone else because they will be able to change the source codes to their own liking and make it work like that. For example, whenever you buy a software, you have to provide some sort of product key or something like that. Like for example, all the antivirus softwares and everything else comes with a product key, right? So if someone gave you the software with the actual source code, what will happen? You can actually take a look at the source code. You can just go to that part where there is a check-in for the product key. If you remove it, there is no need for the product key. Now you can just use the software without even buying it, right? So that's why nobody is ever going to give you the source code. They are always going to give you the object file. And to get the object file, you just have to specify this -c. Later in this course, you will actually learn how to take a look at the assembly part of it, and you can actually hack the software. You can actually learn how to remove that if-else statement in the assembly part. And if you do that, you are basically cracking the file. This is something a computer programmer should know about, and but you shouldn't be doing that because that's not ethical, because someone else put a lot of effort in their product and this is their livelihood. You shouldn't be hacking their software and using it for free. That is a ethical problem, and you should be ethical programmer. Otherwise, karma is not nice. Okay. So yeah, I won't actually be teaching you everything like how to hack and stuff like that. I'll just be giving you the tools, and rest of the stuff have to be figured out by yourself. And that is also a window to the cybersecurity profession. Okay, but anyway, I got sidetracked. And as I was saying, if you put the -c, you get your object file. And if there was no sort of error, this object file is going to be created successfully. If there is any error, you will see the error. You can make another object file for the Fibonacci as well. And after you have created both of them, you can combine them yourself by doing this. And as you can see, we are mentioning the .o file instead of the .c files. You can actually use the .c files as well. They are interchangeable. The difference is .c file has all the C codes and .o file is actually in the assembly. Okay, so you can actually interchange them however you want and it will still work. But you are not supposed to include the both .h and .c. That will actually ruin the whole thing. So yeah, and if you try to compile it without the rfibonacci.c, you will see this warning that there is the implicit declaration, and when it tries to run it, it will not run, and it will give you an error message by the linker saying that this function doesn't exist. You can give it a try yourself. Try to run it like this and see what happens. Okay. So yeah. Hmm. Sorry, I kind of zoned out. So yeah, this is wrong. This will only happen if you do not include this. I forgot to change this part. So if you do not include this, you might get some sort of like error like this. It will say that this particular function does not exist and you have to add it manually or something like that. From whenever you see something like undefined reference or something along this line, you know that you didn't do your declaration correctly, like the hash include correctly. So you have to fix that, and you have to make sure that whenever you are compiling your code, you have to make sure that they are included. So this particular error will happen when you do not include the rfibonacci.c. So if you include it, you will not face this particular problem. So here are some examples of how to do a easier compilation. So far, we have listed all the C source codes in the compilation. We have named them one by one, right? But if you recall the previous lectures, you can remember the idea of wildcard. You can actually make use of wildcard and do it like this. If you write star.c, it will include all the files that has the extension .c. In that case, remember, if I go back real quick, so oh, I went back real back, sorry. So over here, remember we are specifying driver.c and rfibonacci.c. If we just replaced it with star.c, it would be the same thing. So to make your work faster, you can just do that instead of writing all of them one by one. And this will work the same way as if it listed the names one by one. You can also do that with the object files as well. You can write star.o and it would include all of them, okay? And you can also mix them up. Like sometimes you will be provided some object files and a main file, and you can just write something like star.c, star.o. But remember, it will not work if you have the C file of the exact object file, okay? They have to be mutually exclusive. If one of them is there, the other shouldn't be there. But otherwise, yeah, you can just mix them up. It's something to know and something to make your life easier instead of listing all the file names one by one. And another thing you can do, which I already mentioned, is you can mix them up. Like you provide the .c file and the .o file, and it will work the same way. So, and if you notice here, again, we are not including the .h. The .h does not have to be in the compilation code. So yeah, that's it for this lecture. And I feel like the whole process seems kind of messy. Don't worry about it. Try to run it by yourself and see for yourself like how it is done, and it will make more sense to you. Try to create your own separate C files and try to run it by yourself and see how it works. Try to run the example I have given you by yourself and to see how it works or not. If you do not understand this concept, let me know. I will make a better like I will write my own version of codes and show you if you need that. But if you do not need that, I don't want to make a video which no one will watch. I'm just covering the lectures over here. But again, I want you to learn the whole concept of how it works So if there is any gap in the understanding of what just happened here, just let me know. Okay, and I will see you in the next video.